Well, welcome everyone. My name is Conrad Utner. I'm a Senior Application Engineer with MSC Software. I'm excited today that you have joined us, and if you'd like to learn more about MSC Software's Rotordynamics capabilities. I'm excited that you made it, and I'd be happy to introduce you. On the agenda today is a few brief words about the industry and the design challenges faced in the rotordynamics space. The features of MSC Nastran Rotordynamics, which will lead right in from that discussion. A demo model in 3D and 2D. I guess we won't really do any physical modeling, but I will show you the results and some of the setups that are required. And then we'll also take a look at various analysis types that can be engaged in these dimensions. We'll talk about 1D briefly as well, as that is the going type that we primarily see in industry. Then I'd like to talk a little bit about our work with industry partners, the fact that we have a dedicated services team that you can utilize to get up to speed quickly, and the fact that we are in the process and have published and are in the process of publishing a bank of papers in this space, and perhaps we'll end up doing some work with you. So keep that in mind as we go through these slides together. And then so first of all, about the applications and design challenges in this space. MSC Nastran has a big footprint in aerospace, so I guess it's not too surprising that we're working with jet engines and then aeroderivative power gen applications, but the rotordynamics industry is quite large, so we do see additional applications in various industries, and I'm just mentioning here a few: automotive, power generation, and so forth. So anytime you see something fast spinning in the industry, you think of rotordynamics. Interestingly, I guess there's rotordynamics analysis has quite a bit of history, but there's some intricacies, and we'll go through those. But before then, let's talk about a little bit about the design challenges. Typically, people will look for critical speeds and world frequencies. They will want to quantify unbalanced loads or forced harmonic force loads on systems, things such as what happens after blade out. So I guess in this case we're talking about a linear blade out response. What we see here to the right is actually a blade out event. That's not what we're talking about in rotordynamics. I guess that would be more of an explicit event on the right, but I thought I'd throw that slide in there anyway for visualization. Designers care about rubbing, of course, what happens, or that will the rotor rub within the stator somewhere. The evaluation of bearings is a huge topic, so big research is going into that. We do support quite a few setups with bearings. I guess hotly discussed lately have been squeeze film dampers. There's a number of others we'll talk about in the slides to come. And then I guess one big item, of course, is to predict the dynamics of rotating systems, and we're going very close to test setups, and of course it's already very difficult to instrument a single rotor. But if I can only imagine having multiple, perhaps coaxial rotors, having to have to instrument those, very big, lot of money being spent, very difficult to do, and so analysis is a very nice complement here in this space, particularly because we support the ability to have various rotating structures within your system. And then we see somewhat of a renaissance in rotor development. So there's quite a bit of talk about high-profile engines. I guess both Pratt and GE have introduced very new capabilities lately. There's also open rotor concepts being discussed. And that is compounded with general trends in the industry about lightweighting, new materials, composites, additive manufacturing. So there's lots of new, I guess, design space to be covered. And so that leads to, a need to describe rotors, among other geometries, of course, more specifically. What we see in the industry, I guess, very frequent still is the application of 1D rotor models. And that of course makes sense. Traditionally, 1D, that was the only thing was possible were 1D models because of the computational weight. Once you add all the gyroscopic terms in your matrices, then the analysis becomes quite heavy. However, the while 1D rotor models have been I guess used for many years, it's not hard to show that they do fail to capture the action of large flexible disks and blades or non-axisymmetric features. And there are oftentimes there are workarounds. There's very sophisticated 1D models that are being made, but then you run into a trade-off in terms of how much time do you want to spend on your 1D model if you can just go and turn up the dimensions. When you do that, when you get into a 3D model, which I indicated here on the right, going from just a 1D line here to a 3D model, what of course, as I mentioned, the computation becomes pretty heavy, and along with that comes a very nice Nastran feature. Nastran has been, MSC Nastran has been developed with quite a few dynamic reduction techniques, and those can be implemented or within Rotordynamics as well. So model reduction becomes a big topic once you step up into this domain, and we'll talk about this a little bit more in slides to come. So first of all, though, let's talk a little bit about the features, and this is just an introductory slide in terms of, well, first of all, let's talk about the the governing equations that are actually being solved, and depending on the existence of symmetries in your rotor and stator models, you can then select the appropriate reference frame to do your analysis in, and MSC chose to provide you with, or arm you, I should say, with two different formulations, one in the fixed reference frame, the other one in the rotating reference frame. And here the graphic indicates the relation between the two, and where in essence the fixed system, the difference between the fixed and the rotating system is this angle phi that is defined by the rotor speed times, the angular velocity times time, and you see here the corresponding transformation matrix that is used in the formulation. So the equations are actually derived from Lagrange's principle, which in essence says that the work done is a combination of kinetic energy, potential energy, and diffusive energy. And when you go through the derivation, and I guess we do have this pretty detailed in our reference manuals, you arrive at a equation that's pretty common, I guess, in the dynamics field. I guess it's a little bit more augmented, but you see here so G are just the generalized degrees of freedom. So think of displacements, and so you have so there's the typical F equals ma is hidden here, of course, with mg double dot equals F, and then you have the velocity term, which is multiplied by a damping term, and then you have stiffness times displacement. Of course, we have here the gyroscopic matrix now because we have a rotating system, and there's damping that can be applied either to the stator or the rotor. And then if you do apply damping on the rotor, then you end up with a circulatory matrix, and in addition you also have the differential stiffness expressed here as well. So typically, in typical equation that you would see in the dynamics world, again augmented with the fact that now we have a rotating system. Then there's the equations in the rotating reference frame, where now the geometric matrix becomes the Coriolis matrix, and we have also an additional centrifugal softening term in the formulation. And then there's so these are the constraints to obtain then a time-independent left-hand side is that the non-rotating, I guess, fixed component of the model have to be axisymmetric. But again, these are considerations that you then engage when you make your model and to decide which of whether rotor or stator can be axisymmetric or cannot be axisymmetric, and then you make the appropriate choices of reference frame and analysis assumptions. So the tools that enables you, I guess we do support analysis in 1 dimensions, 2D, and 3D. The 1D models, I believe, are still very important because, first of all, they give you a first step into analysis, and also the ability to model in 1D allows you also to verify your existing legacy models, which, of course, is the first step that you would typically take if you're considering new methods. But then you have the ability to represent your rotors and your stators in 2 dimensions and 3 dimensions, and, of course, have the ability to represent much greater detail, which is indicated here on the right with some of the images. This leads to a more realistic prediction of the dynamic behavior of your system, and you have a greater analysis resolution down to blades and disk modes, which you do not get if you are working in 1 dimension only. And this allows you then also to observe coupling behavior between shafts, disks, and blades as well. Additional features in the fixed reference frame are the fact that you can define, and I mentioned this earlier a little bit, that you can define multiple rotors within one system. So you see here looking at the high turbine and the high compressor shaft, as well as the lower speed low pressure turbine and low compression system, where in essence you end up with 2 rotor speeds, and you have the ability to express those. You can mount the rotor with to your static structure with a number of different elements. I guess one example mentioned here is a spring damper element. There are various nonlinear elements that you can use here as well. And then the one interesting thing here is also that you have the ability to condense multiple rotors within multiple superelements. So there's a lot of flexibility given to you here to have very complicated rotor systems, and then use component mode synthesis to reduce model size. And that, of course, becomes very important when you're dealing with larger systems, perhaps even parts of the airframe if they are included. Yeah, and then, of course, you have the ability to study the effects of non-symmetric and nonlinear bearings and supports. So a lot of research and study goes into this. Some additional features on the rotating reference frame is you can also have non-symmetric components and such as a crankshaft, so as shown here on the bottom right, or single turbofan blades as shown on the left, or helicopter blades for that matter. Multiple rotors can be included in the analysis in the rotating reference frame as well. However, it needs to be, the one limitation here is that they need to be all at the same rotor speed. That's different from the fixed reference frame. And then you have the ability also to engage in a vibration analysis of blades and disks to obtain then these coupled modes, as I mentioned earlier, between shaft, disk, and blade. So the supported elements are actually quite varied. You have the ability to still lump concentrated masses in cases where the geometry is just, where there's a trade-off where the representation of the geometric complexity does not really warrant going to higher dimensions, so you can condense areas. You have then your traditional 1D elements, beams or bars, as are typically seen in 1D models. And then we are talking about the 2D axisymmetric harmonic formulation, which uses axisymmetric elements, but they're then augmented with a PAXIM H card, which is an azimuthal Fourier expansion that produces a 3-dimensional displacement field. And we'll take a little bit closer look at that in a minute. But beforehand, let's talk quickly about the 3D elements. So in 3D, you can use quads and triangle elements as shells, and tetrahedral, pentrahedral, and hexahedral elements in 3D for 3D solids. And it should be mentioned that all of these element types can appear in the same model, and they can all be coupled with one another, so giving you a lot of flexibility. On the right, I'm just pointing out a few modeling tricks here that can be used. For instance, there is an RBX 3D element, for instance, which connects the 2D axisymmetric harmonic element with the 3D world. So there are a number of advanced connectors that need to be implemented when you do go between dimensions. A few other examples mentioned here, like the CON-M2, which is a concentrated mass that could potentially replace a blade, or any structure that you choose not to present fully in its full geometric extension. The supported solution sequence are also quite extensive. We're going from 101 statics, which you would typically use for your 1G loading verification, or just a simple cantilever test, if you will. 103, that typically is also for verification purposes, just to make sure that none of your parts are flying off, and also just to look at the behavior of the rotor with at 0 rotor speed, just to make sure that you have consistency as you go into your complex eigenvalue or frequency response analysis. And those are then the next analysis steps. So 107 being direct complex eigenvalue, and then there's also modal formulation with solution 110. Likewise, in the frequency response side, there's also support for direct and modal frequency response analyses, which introduce just additional efficiencies. The modal formulations have the ability to solve problems much faster. Of course, you have the trade-off there that you need to ensure that you have the appropriate number of modes captured. But once you do, the analysis speed is much much improved, and we'll also see some of those examples later in this presentation. Then we go into the direct transient response analysis with 109 and various other transients. So before I talk about the transient solver, so let me also point out a very new solver, the nonlinear frequency response solver. So frequency response being traditionally linear, we introduced now a formulation that allows you to specify moderate degrees of nonlinearity within those models. 129 being our legacy transient solver, and now 400 is really what we would like you to use. This is the nonlinear solver that was ported over from the MARC environment and is now resident within MSC Nastran. And of course, that allows you then to use a lot of these nonlinear elements that can be used for bearings and any nonlinear effects that you might encounter in your models. Solution 200 is we're currently, the support for optimization is currently limited to stators and bearings, but this is an ongoing development effort, and you will see in advances here within the next releases. So let's take a brief look at a demo model. So this is a very simplified model that we use from the literature. So Nelson, McVaugh are credited with this rotor. It's not very complicated. I guess it's sort of our 101 example that we will throw at you if you are interested in starting to model with this. Of course, the rotors that we typically deal with are much more complicated, but it does serve as a pretty nice introductory example. What I'm also highlighting here is our new pre-post MSC Apex, and which we use increasingly for its great utility in the geometric simplification area. So we just throw 2 slides in here, and you see, of course, primarily hexahedral elements representing this rotor, and then just a few, 2 bearings that are shown here. We're not going to really go into detail, but there's some RBE elements that connect, and there's also C-bush elements that are spring damper elements that in essence represent the bearings against their counterparts. So this is just a rotor, an isolated rotor on a test stand, if you will. And we use also Apex to carry out solution 103. This is actually works in an integrated fashion. You don't even need to specify 103. It's just a real Eigenmode solution. And we see here on the left is the first bending mode, and on the right the first torsion mode. Now, I guess I'm going to throw something at you, and I guess for those of you not familiar with MSC Nastran, this may be a little bit of a step change, but I think for those of you who are familiar with MSC Nastran, so this is an input deck as would be passed on to MSC Nastran, and to change the earlier model, so the earlier 103 model that I just showed, you would make a few changes to your input file, and so most of the analysis content is actually captured here in the nodes and elements. What we're adding is, of course, we're changing 103 to 107 to prepare for an asynchronous sweep across rotor speeds. We changed the method, and we now define a rotor and as well as the frequency sweep in these two cards. Notice, for instance, as one example, the rotor is specified via property. So properties 102 and 103 are the two properties used here in this particular test models, and they indicate that they're part of the rotor. We also specify a forward and aft bearing, but those are, of course, were already specified in the 103 model. What I'd like to also highlight with this slide here is that any particular rotor that you build after that could be wrapped around with this script, if you will. And what I believe in, these scripts have a big advantage in that you can apply quality control against various rotors that you apply quite nicely with the clean organization of Nastran decks. So when you solve this model and you see the behavior of the whirl frequency with respect to rotor speed, and what we found in this particular model is that the backward whirl mode actually decreases. The eigenfrequency of the backward whirl mode decreases as rotor speed increases and the forward whirl increases. So for those of you not familiar with what is forward whirl and backward whirl, you see here the definition on the right, and I'm also including here a quick picture of what, in essence, what we are showing here is the M1, if you will. So that is a backward whirl, where in essence where the whirl goes clockwise, and the rotation of the rotor is actually counterclockwise. So, of course, we didn't really need to solve the entire sweep. If you are just interested in critical speeds, you can just engage a complex eigenvalue analysis, and Nastran would then produce the critical frequencies, which are the intersections between the whirl frequencies and the engine speed, which is indicated here by 1p. Accordingly, you can then also visualize the corresponding mode shapes, and we recall from earlier the first bending mode, and then which of course is the this backward whirl mode that we looked at, and then the torsion mode, which is shown up here, which of course does not have any frequency dependence. Let's step into two dimensions and how this works. So I mentioned earlier that this is 2D axisymmetric harmonic, which indicates that there is a Fourier expansion in the azimuthal direction in play, which leads to a three-dimensional displacement field. So this is somewhat of a surprising feature of this 2D axisymmetric formulation. And by the way, here's also again repeated the RBX 3D element, which establishes the connection between the 2D axisymmetric harmonic formulation and the 3D world. But you see here you have a sine cosine contributions to your 3D displacement field, and so in a practical sense, you see if we use that same rotor that we have been discussing to this point and make an axisymmetric model of it. So maybe let me turn on the laser pointer. So in essence, we're making an axisymmetric cross-section, which is represented then here as in an element representation below. We can then take a look at the critical modes, and we have the ability to animate those. We could, of course, just post-process the axisymmetric harmonic element, but you have the ability, so this would be at one at one angle. You can, of course, process any angle that you like, and you see it now. What happens is you evaluate at more and more angles, then you get a full 3D representation, and this is what we had animated just a second ago. Also, just for completeness, let me also show you again the full animation of this particular mode from two different points of view. So interesting aspect to the 2D axisymmetric harmonic elements are also much lighter, so they are have great practical value in that they solve much faster than their 3D counterpart, but also already give you a 3D feel for what you can expect to see when you go to 3 dimensions. So additional analyses, we talked about the linear frequency response. In this case, we applied an unbalanced load, and then we found a resonant frequency as we swept along. So the loading increases, since it's an unbalanced load, and increases quadratically as to be expected. And then at a particular frequency, you will see then a harmonic response. On the left-hand side, I believe the damping was 0, and then as you increase damping, as we would expect in any dynamic analysis, the displacement peak decreases, and the width of the response widens. And next analysis type is transient. So in this case, we applied, a load, a time-dependent loading, and applied also external damping. And you see here that so on the left we have the loading, on the right we have the displacement response, and we see there are some there is a response shown here at a particular frequency. And if we're actually plotting the response with respect to both, well, with respect to time, but if we're plotting displacement and frequency, we see that the system responds at the forward whirl critical speed, which is to be expected. Another aspect, we talked a little bit about nonlinear bearings. So we have the ability to, for instance, here use NLRGAP, which would be interesting to use in a scenario where you have a clearance issue, for instance, or a rubbing issue. So you can say, for instance, well, I know this rotor responded this way when it was isolated, but now we are it actually is within a casing or within a bearing, but the displacement is going to be cut off at 0.05 units. So you have the ability to express this with an NLRGAP element, and then can compare the responses, and then also, of course, look at what sort of forces would then be imposed on the rotor if you impose such a nonlinear gap, in essence, going from no resistance to full resistance at a specific displacement. Nonlinear frequency response, so this is this very new capability. Here we are showing, again, an unbalanced load, just looking at the load, the quadratic load, as we increase frequency. And then we're showing here on the, I should point out my laser pointer. So the quadratic increase of an unbalanced load, and then we're showing here what happens with spin up and spin down. Of course, the response will vary, as in a linear analysis, the spin up and spin down responses would be the same, but as in a nonlinear system, the starting points are, of course, very important, so you do get different responses for spin up and spin down. And here on the right, we're just then looking at a nonlinear stiffness, in that we make the displacement, we have a relationship of displacement cubed multiplied by a constant, and what we're doing here on the bottom is we're just showing that we're comparing the linear response with an increasing with an increasing constant here that is multiplied by displacement cubed. And you see here both spin up and spin down are compared, and sort of give you a feeling for how the system responds to this nonlinearity. Another concept, and that becomes very important, I mentioned it very early on, is the ability to use superelements with rotors. And so superelements allow you to segment your FEA model, and each one of those segments are in essence independent FEA models that all have their mass damping and stiffness matrices, and to which also constraints and loadings are applied. The superelement itself is defined by analysis modes and by an analysis and an omitted set, with the subassembly. Well, the analyses are possible at each one of the collector nodes. So if you look at this airframe here on the right, this is one particular way on how you could segment this particular FEA model into superelements. There's, of course, many different ways possible, but this is just one chosen way. But any collector analysis can take place at any collector, provided that the upstream superelements are reduced, and then you have the ability to perform analyses either on the superelement level or on the subassembly level or on the full system level. The fact that we support superelements in essence gives you the ability to integrate these analyses in your entire airframe. And here's another feature of this that is, so for instance, let's say the right engine, we decide to reduce, or in a creation run, if you will, produce a superelement for the right engine and then integrate it into the assembly. We could, of course, do the same thing with the left engine. So we make a left engine superelement and then connect that with the airframe. There's a nice feature within Nastran that allows you to actually use transforms of any particular superelement, of any particular rotor superelement, and that would then allow you, so I try to indicate this here by saying, well, you could still, in the first model, we would use two different superelements for each left and right engines. So left engine would come from one superelement, the right engine would come from one superelement, the left engine would come from the other, but then there's the ability to actually use a transform, so we could use a mirror image and a translation of this superelement, and in essence use the same superelement to represent both engines, so one being a mirror, a translated mirror image of the other. That, of course, means computational efficiency, so you, instead of two superelements, you're only carrying one, and of course you only have to build one, which then also means workflow efficiency, so you only need to do half the work. And that was quite welcome, because we did realize that people actually did spend quite a bit of time to make the mirror image or secondary superelements before this feature came around. Finally, I'd like to talk to you about the work we're doing with industry partners, and here's one study we published with SAE last year, and here we're showing the difference between on the bottom left, we're showing the difference between a classic rotor approach and a full 3D rotor. The classic rotor is 3D elements, 3D traditional elements, and has gyroscopic terms introduced by point masses, and it's indicated here that if you are not careful about the placement of those point masses, you might miss some important modal behavior. So in this case, it shows that the third backward and forward whirl mode are completely missed by one of the traditional models. On the right here, we have the difference between a 1D model and a 3D model, so very different responses. And here on the right, we see the comparison between the axisymmetric harmonic and the 3D formulations, which are very close. In this case, I guess in the defense of the 3D rotor, this is was actually on a axisymmetric rotor, so we would expect those to be quite close. The next study was, actually is another result of the same study, and this just shows that we have, when we do analyze the rotor coupled with the engine casing, that you no longer have this expected, this clean, isolated rotor behavior of clean forward and backward whirl modes and so forth, where you actually do have coupling between the system. This is not the actual engine used. I just thought I'd throw a picture in here. We didn't quite have time to get the clearance to have the actual picture shown here, but I think this picture does it justice, and in essence is the indication that you have the ability to investigate the coupling actually between the rotating and static systems. On the right here you see too how you have the ability with MSC Nastran to extract the kinetic energy of each one of these mode states. You can also extract the strain energy. There's other components as well, of course, that you can pull out. Another study which actually was just accepted by Turbo Expo, which we'll present this year, indicates the computational advantage of superelements. Just as a very brief comparison, so we had various models that showed that actually, well, let's go to the middle column here. We had various models that showed that represented the same engine, the same engine, but of course using different superelement configurations. So you see this is the full engine without any superelements. And then this is the probably the most efficient one and the one with the lowest error. We also indicate here that we are very much in control of the error. And so in sum, so I guess to reduce the rotor would take about 2 minutes, 40 minutes for the casing, and then another 2 minutes to solve the Campbell diagram, and another, I don't know, half a minute, if you will, to do the frequency response analysis, versus a day and a half and 2 days with a full engine. And then, of course, the comparison here on the top, you see that these results are very close to one another. But you see that there's leaps and bounds that you can improve computational efficiency by using superelements. And then there's a third paper that was presented last year at ASME IMECE, where the rotating reference frame was taken into closer consideration. And so here we're looking at isolated blade modes in the rotating reference frame. We'll look at fixed modes, modes at the fixed reference frame on the right, and then unbalanced loads with using point masses on the rotor system. So there's a lot of comparisons between fixed and rotating reference frame, and also what happens when you reduce, when you actually do away with blade effects. So nice paper if you want to get a feel for what does it really matter? Is it important to represent my rotating system in higher dimensions? And so I guess with that, I'd like to just leave with the final thought that we are very interested in partnering with industry. One of the strengths I think that we would like to build into the product is that it is relevant to your work and to the industry that you're in. We have very close relationships with industry, and as I said, we would be very happy to work with you. Thanks for your attention.